Good afternoon, everybody. It's time for another wonderful afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. And I got a lot to do with you this afternoon. Plus, we're going to do an interesting experiment, not just the one in the lab, but I'm going to do an experiment with you. It's called Breakout Rooms, but that's later on. All right, couple of things. First of all, hopefully you've been checking your email and also looking at the announcements in Blackboard, wrong school, D2L. Everybody see Chem 170 test number one information on your screen? Thank you. All right. This is an announcement in D2L, and also you got an email. Next Wednesday, the 17th, I'll be giving test number one online. What you'll be doing is you'll download a password protected PDF file from the assignment area D2L. That will be available the Tuesday before that afternoon. Since it's password protected, you can't open it up yet. And on next Wednesday, right after our class, I'll send out an email with the password to open up that file. You'll have until the next day, Thursday, 10 a.m., to finish test number one, upload your test answers to the assignment area of test number one as a single PDF file. You should take about 40 minutes. If you need a little more, don't worry, I won't tell. Take up to about an hour, hour and 15 minutes if you really need it. But you shouldn't. The way I write tests are, if we had been in a face-to-face class, I give my class 50 minutes, 50, 55 minutes. If you've done the practice problems, studied a little, most of you are going to be done in about 35, maybe even 40 minutes, usually about 35 to 40 minutes. Almost the whole class is done by then if we were face to face. Now, test number one has 10 pages, 14 problems. Relax, I read a test, so if you've done the practice problems, studied, obviously you had to if you do the practice problems correctly, you'll be done in 35, 40 minutes. I don't like to use chapter numbers. I use functional groups. And I could have also put down here hydrocarbons. It covers hydrocarbons, alkanes, which are hydrocarbons, cycloalkanes, alkenes, double bonds, alkynes, triple bonds, and I'll finish up today aromatic compounds. This test, as all my tests, and I should also include the final, is not open notes. I have put certain things the way I write my tests now online that I'll know if you went into your notes or not. So please don't. You shouldn't. This is I could do things where uh, there are ways of doing with a cell phone and Zoom where I have an eye on you, but I'm going to do the honor system. Please be honest. If you don't, and I think you've cheated, I will do what I have in my test, I mean, my syllabus, which I will write to the letter to the Dean of Students, also my Dean of Math and Science, and also you get a zero for the test. So please don't. Now, points breakdown for test number one, 13 points general knowledge, like how many bonds to carbon, that's general knowledge. Hopefully, you all know four. Then nomenclature. And what I mean by that, there are two types of nomenclature questions. One is here's the structure, give the IUPAC name. The other is here's the name, which can also be common name. There's only one I asked you to learn acetylene this whole chapter, and draw the structure. And finally, the last part, 47 points, is reactions. And a reaction problem, there are two types. One is here are the reactants or starting materials. What's the organic product or products for the following? I only have one problem on this test under reactions that are here's the product and the reagent you react it with, what would be the starting material? Now, I don't know if I attached to this one, I don't think I did, but in D2L, there are files I've shown you how to take and make a upload a test as a single PDF file. If you have a scanner, you can do it directly from your scanner. If you don't have a scanner, then you can use the apps. There's scan or something. It's in my, I have a Word file describing how to do that. You can actually do it in Windows if you have a bunch of JPEG and combine them, but there's an easier way. Just use the app for yours. There's an app called Scanner and Scanner something. I can't think of the name right now. And next Monday, I'll do a review for test number 1 in our Zoom meeting. Now, what I've done for online courses is next Wednesday, we'll still have our regular meeting in a lab. In real life, if we had it, we'd have a test and I'd have some time to go over material and then we go to the lab. But we're not going to do that. We're just going to have our regular Zoom meeting with lab next Wednesday. And afterward, you'll have from roughly 4 p.m. till 10 a.m. the next morning to hand and finish the test. That way, because of things I've learned due to our, and how should I say, our situation due to the virus, that sometimes students get phone calls like they have to go into work. I've had students who work at nursing homes, who have worked in pharmacies or at hospitals, and they have to go into work to help because somebody's gotten sick. They have to cover a shift. And that way you have plenty of time to do the test and upload it. If you take a little more than an hour, that's okay. One of the things I've learned is if you don't cheat, and you shouldn't, that either you know it or you don't. If you know it, you're done in 40 minutes or less. If you don't, well, you can have all the time in the world. It's not going to help. So hopefully you've done the practice problem. Do the practice problems. And that's that. Any questions about, any questions about test number 1? And I'll talk a little more about it on Monday or answer any questions. Don't forget, tonight I have my office hour from 6 to 7:15. If you ever have any questions, ask. Also today after lab, I'll stick around for a couple of minutes if you have any questions too. All right, now I had promised on Monday that today I will do right now, and I'll be cutting this out from the video. Let's see. I don't have any other practice problems. There's one practice problem. Email me and I'll send you the link. But it's more geared toward 2 semester. So some of the questions aren't germane to what I would ask on a test, like things dealing with mechanism. In fact, that other site that's pretty decent was created by my research advisor at Michigan State. My professor is Dr. William Roosh, and he's got a nice site, but that's geared toward a 2 semester organic. Now, if you want a practice problem, you can do your own and then come to me and either after lab or in my office hour. And did I do it right? If you show it to me, I can tell you, or email it to me as a PDF file. And all you have to do is, I've been doing it all semester. Say you want to practice the following, then I'm going to go into something else afterward. Let's get to a white page. And you're right, Joshua, any good practice is good practice. Now, say you want to practice the following reaction. And you have about 11 general reactions you have to memorize, and that's part of organic chemistry. Well, how do you practice this? Well, you got a double bond, you're reacting with HX. Remember, X here can be chlorine, bromine, or iodine. And what do? I say, well, pick a number between 1 and 10. Oh, 5. So I have 5 carbons. Now, some of these you might get yourself in trouble because you'll do gray areas. I stay away from that in class. But for the most part, I'll put the double bond here, and hey, I'll put a methyl group. And you know how to put the hydrogens in. Then what are you in the mood for? Chlorine, bromine, or iodine? Oh, let's do bromine. And then now do this. Well, how do you do it? You got the general reaction here. Look at what's different, double bond. And what does the general reaction tell you? You break the double bond, one carbon gets H, the other gets X, and it follows Markov-Nikols's rule. That is, the carbon with the most hydrogen gets the hydrogen, the other gets the halogen. Well, do you break carbon-carbon single bonds? No. 1, 2, 3, 4, 5 across. Here's my methyl. And then these are my 2 carbons double bond. This has 2 hydrogens. This has 1. Therefore, the hydrogen will go there. The halogen will go there. And I know there are 4 bonds to carbon, and I can put it in my hydrogens. And that's how you do your own problems. Say you wanted to practice it again. Well, I want a ring. Well, here's a ring with a methyl group, and I'll do HCl, and you do the same thing. And you can make as many of your own practice problems. Secret, here's a secret. When I'm going to do an example, I think, am I in the mood for 4, 5, 3, 7? How many carbons? Do I want to put a methyl, ethyl, or whatever on there? And what functional group am I practicing? And that's all I'm doing. And what I'm saying is you can make up your own like this, and then you can do them and send them to me as a PDF file, and I'll be able to tell you which ones you got wrong or right. Okay? Does that help? By the way, for those of you who are dying to know, the correct answer to this problem would be this, or you could have written it this way, which is perfectly correct for my class. All you're doing is rotating the ring, like my hand, 180 degrees. So does that answer that question? So now you all know how to create your own practice problems beyond the ones Dr. White gives you. The nice thing about the ones I give you, you got the answers. But you can send them to me, your own practice problems, and I'll know if you've done it right. All right. One of the things I believe I said I'd do today, and I better do it today because I always try and keep my word, is I would like to teach you a method I developed a number of years ago that eliminates test anxiety like that, actually quicker than that. And it works. Over the years in chemistry classes, Chem 170 and others, it's been quite effective seeing students who have had test anxiety go from getting F's, D's, and C's to B's and A's. And it's, I can think of an example in Chem 170, but the one I'll tell you about is the first time I developed the method. Throughout my life, I've been very lucky. I've been able to solve problems quickly when there's a need to do it quickly and effectively. And there was a need. Now, years ago, I was teaching Chem 112, General Chemistry at ECC. It was the night course. And we had Monday, Wednesday, like here, lecture, then lecture lab. And I gave back the tests in class, and I went through the test answers. Well, I had a student in that class who was doing all the practice problems, coming to my office hours to see if she was doing it right. And I'm thinking, boy, this is going to be one of my top 8 students, which makes me feel good because I like to see students succeed. So test number 1, this is in Chem 112, but I've seen this happen in Chem 170 also. And I used to wait until after test 1 to teach this. Now I decided to do it before. And I graded the test. I look, after I graded everybody's test, I'm putting into the grade book. She barely got a D. I said, oh, I must have made an adding error or something. So I go back and regrade the whole test, no error. Well, I hand back the test. And after class, we had a lab. We did the lab. And after, if I was at ECC, I'd be doing it for our lab. I clean up, put things away. And she comes back in, and I should tell you, I have two sisters. One's 7 years older, one's 7 years younger. Yeah, I'm in the middle. And the younger one can turn her tears on like click, click. And I learned how to deal with that. And so she comes back and says, look at my test. Look at the answer. I know that's wrong. What's wrong? She starts crying. So immediately I tell her, stop crying, take a deep breath, because I can't help you if you're crying, which is true. And I'm thinking, how do I help the student? Here I have a very upset student. I got to do something now. Well, it turned out about a year or so earlier, I read a great book called Influencing with Integrity by Jeannie Laborde, Dr. Laborde. And in there, she has a method how to put your, she calls it your mind in a positive resource state. Athletes call that being in the zone. I think you've heard that term, being in the zone. So that method is pretty clunky. It works, but it's not that easy to do, especially during a test. And I'm thinking, well, how can I help the student out? And I'm, all right, let me just take this method and shave it down and modify it so it's quick and easy to use and you can do it during a test. Well, I did, and I taught her that. And then I said, Monday, let's practice it. Make sure you got it. It worked. Next test, she got an 8, one of the highest scores in the class. And the rest of that in the final, she did the same. And just like this class, that class, the lowest test of the 4 I give is dropped. So she got a high A. Well, years later, she came back to see me, say hello. And I said, how you doing? She said, well, I wanted to come back and thank you. I said, you're welcome. Now, what are you thanking me for? Said, next week I start working at a hospital as a nurse. And so all because of you. And I said, whoa, 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 it's because of you, not me. Said, you don't understand. I said, well, tell me. What I don't understand is, remember how you taught me the method? And I tried to come up with names, but it just comes down to the method. And I said, yeah, it worked for you. He said, yeah, it really did. I was barely getting by in my classes. Now I started getting A's. By the way, the method works in other classes too when you're taking a test. And she said, that got me into nursing school. When I was in nursing school, no problem with the test because she also taught me how to study. That class I also teach, do practice, problem, practice, and repetition like I'm doing here. And she said I got through nursing school quite well. And because of that, I'm starting as a nurse. Thank you. I said, you're welcome, but you really did the hard work, not me. She said, no, you helped me. Okay, I'm not going to fight with her. I don't fight with students. And I was very happy. What's the method? The method is very simply bring back a very positive memory. When you bring back that memory, first of all, you should bring back the picture in your mind when that memory happened, what was happening. Bring back the sounds of what was happening in that memory. And most importantly, bring back what you were feeling. It should be a very happy memory, and you'll feel good. And you let that feeling go through your body. By doing that, it puts your mind in what Dr. Laborde calls a positive resource state. I calling it put you in the zone. And you still got to learn the material, but your mind is now working at the optimum best it can, assuming you've learned the material. So let me show you how this works. And excuse me, back when I was starting in industry, I just got my PhD and then I was a postdoctoral fellow, got a job, started out brand new in industry. I have this project I'm working for. I had a great boss, Dr. McDaniel, Bob McDaniel. He was really great. He left the company about 2 years after that. And then I became the youngest section head in that whole company worldwide. But anyways, I had a project and I'd set up a reaction and follow it during the day. And following it means analyzing it. That took about 5 minutes every hour. At the end of the day, I'd analyze it, clean up, and think about what I do and go home. Well, I had a lot of time each hour, between hours. So I went to Bob, because who I am and my personality, I said, I got all this free time. Is there another project I can work on? And Bob, knowing something, he said, why don't you ask Sid Shapiro? And Sid Shapiro was my mentor. At that point, I was in my late 20s, and Sid was already in his late 60s. He'd been with that company like 35, 40 years. He helped start certain industry in the chemical industry and fatty amines, and I'll talk a lot about that later in the semester. And Sid was sharp. He passed away in '95, unfortunately, but he was my mentor, and I actually carpooled with him for a year, and he used to uh, test me all the time and teach me stuff. So Bob already knew what Sid was going to say, and Sid did. He said, "Oh, you want to do another project?" And Bob asked for my advice. Well, you should do this one. And it's a chemistry I don't teach here, but it's called reductive amination, a way of doing a reaction to make a certain type of product. And for at that point, for over 35 years, both at the company I was working at and other companies, they were trying to make it work, and nobody could. They'd been working on it for decades. And I love a challenge. So that got me all excited. Something else nobody else can do. Yeah, I'm going to do it. And I have done that. And so what was the problem? Well, how many of you are familiar with the term percent yield? Hopefully you all had that in undergrad. That's the how much you make divided by theoretical amount you could make. Well, in the chemical industry, if your percent yield is 90 or above, it's not economically feasible. If you got a real high profit margin, maybe you go a few points like the 87. But realistically, any senior manager in the chemical industry, if you're not above 90 and above, we're not going to even mess with that. Well, when you ran this reaction, all you got was a yield of about 50%, which is awful. So I ran it and saw what happened. Yeah, I got 50%. How do I know I got 50%? Well, you analyze it. How do you analyze that? You take some of the reaction, you put it in what's called inject it. Notice how I was injecting it like I would if I was still in the lab, into a gas chromatograph, which is called a GC. If you ever see the CSI programs, you'll see them inject something, or now they have an automatic and auto injector. And then you'll see on a screen a little lines, and they can tell what percent different things are in a sample. Well, back then we didn't have computers like this or screens. We had a dot matrix small little one printer that printed on a tape the different times what's called peaks come out and what percentage of the sample. And by knowing your compound, what you're trying to make the time, you can find out what the percent yield was, how much you made. Well, I ran it and I got 50%. And then I know how to, back then it was avant-garde, now it's passe. I knew how to think outside the box. I'm thinking, how do I sell? I said, I think I know how to do it. I ran it, I got better, I tweaked it some more, and I thought, I think I got it. So I ran the reaction, and after a couple hours, I injected it. And this GC was in my lab where I had my desk and bench, because I was still a bench chemist. And behind there was, I'm closing my eyes because I can see it now, like it was happening right now. By the way, this happened about 1982, 81. Wow, that's a long time ago, and it's still like it's just happening now. It was an ugly green cinder block wall that when I became section head, I had it painted. Oh, I hated that color. And I injected it. I went and sat on my desk, and I was doing something else. And all of a sudden, I hear the dot matrix pinner going like this, making noise. Ooh, it's done. I go over there. I look at the tape. I look at the one time, and I see the number 96%. I nailed it. Yes, I nailed it. Right now, I did it. What nobody else could do for decades, I pulled it off. Well, at that point, I didn't tell anybody because I ran it 5 more times. That's something Dr. White always likes to be safe before you start publishing results or spreading the word. I did it. And each one, it was about 96 to 97%. I nailed it. Right now, I feel good. You can see how I feel. And that's the method. The method is close your eyes. Don't do this while you're driving or operating heavy machinery, and bring back that time. I can see that GC. I can see that wall. I can hear the dot matrix printer. My hearing was better back then. And I can see that number. And I remember I feel, you did it. Right now I feel that way. And I'm happy. And my mind's this maximum resource state. I'm in the zone right now. You still got to learn the material, but your mind's ready to use that material to solve anything or what you need to do. Now, what I'm going to ask you all to do is try it. Hopefully you're not driving or anything like that right now or operating heavy machinery, but close your eyes. Go ahead, close your eyes. Bring back a real good memory. Bring back what you saw. Bring back what you heard. And now bring back what you feel. Now, if you had a really good memory, you probably have a smile on your face right now. If not, you got to find a better one. You can open your eyes now. But anyways, and how does that work? Well, I have found over the years teaching this, the slowest student I've ever seen bringing back a memory that works is about 5 seconds. Say you're taking a test, and it doesn't just have to be my class. Close your eyes, bring back, see, I already brought back the memory. It was about 2-3 seconds. And bring back that memory, the sight, the sound, I did it. And your feeling, and let that feeling go through your whole body. And now you're ready. You're no longer anxious. Slow student, 5 seconds. Let's say during a 50-minute test, if you were in face-to-face, you do that 20 times. Most people don't, but let's say you did. 20 times 5, that's 100 seconds. That's less than 2 minutes. Would you spend less than 2 minutes over 50 minutes to be at your mental peak? I would every day of the week. There's not even a question to think about. I would. That's how you do it. Now, listen carefully. First of all, I never, ever ask a student what's their memory, because sometimes it's very personal. But I have had students share with me. I do, and I have created a test I can do that I do one-on-one that I can tell without you telling me your memory, but I ask you to bring it back under a certain condition. I can tell if you have a strong enough memory. And sometimes it's like you need a better memory. And it works well. And the last thing, about the last 4 or 5 years, I don't know why, and I'm not a psychiatrist or psychologist, but some students, you see them start to bring back the memory and all of a sudden they shut it down. I'm not allowed to, something in their mind doesn't allow them to be happy. And I have to convince them it's all right to be happy. It's all right to feel good. I have no idea, but I've seen it over the last 5 years, at least 8 or 10 times. I've had students who won't let themselves be happy. Don't know, that's not my area of expertise, but we were able to work through it. I will tell you this, I had one student years ago in Chem 170 who kept on saying, my life has been the most horrible life in the world. I have nothing happened that ever happened in my life. I said, that can't be true. At least for 1 or 2 minutes, does something make you feel good? Then about a week later after that, she comes, I found something. And she said, I said, what? Oh, good. And we tested and it was really strong. And she shared it with me. I didn't ask, I'm not going to use names, so you don't know who it is. But anyways, she wanted, when she was about 10 or 11, she always wanted to be a fairy princess for Halloween. And her parents finally got her the costume. She put it on immediately, stood in front of the mirror, and that was her happy thing. And she could bring back that memory. And she went from barely being a C student to being a high A student in Chem 170. That's it. If you need help, come to my office hour. It works. All right. Any questions? All right. Now, the other thing, I don't know if I mentioned it, and bad Dr. White if I didn't, I like to go through the Alkenes and Alkines practice problem set now. Remember, I'll do one page at a time. If you have any you want me to do, let me do it. Tell me you want it if I don't do it myself. And today we'll go a little longer. We'll still get out by 3-ish or so because I taught you. There we are. All right. Everybody see the Alkenes problem set on the screen? Thank you. All right, let's look at these. First one, remember, test number 1 will have nomenclature problems, which this is. Give the IUPAC name for the following. And if we look at this, what do? We look for what's different. Double bond. There are 4 carbons, and the longest chain contains both carbons, double bond. That's butane, but it's a double bond. Drop the A on the ending, put an E on E. What's the lead carbon, the one closest to the end of the chain? That's 1. Now, when you have two of the same atom or group on one carbon double bond, you don't use cis or trans. And if we look at C, double bond, I'm showing the stereochemistry, but this carbon still connect this one to this. And here we have 1, 2, 3, 4, 5 carbons. It's pentane, double bond, pentene. Which carbon of the double bond is close to the end? This one's carbon 2. It's 2-pentene. Notice we have two carbons and they're on the same side as this line. I'm trying to do it with my pointer because I can't write on a PDF file. And that's cis. Now, if you notice down here, let me move this out of the way. We have two methyl groups, even though one is part of the chain, one's called methyl. 5 carbons, pentane becomes pentene, 2-pentene. There's a methyl group on carbon 2. This is 1, this is 2, 2-methyl pentene. And I'll get your question in a second, whoever's about to ask a question. Why not cis or trans? Because on the carbon of the double bond, there are 2 CH3 groups, and you can't have cis or trans. Does someone have a question?
Yeah, I keep thinking that the CH3, CH2 is an ethyl group there.
I mean, right up here in C?
Yeah, why do I keep doing that?
All right. Have you ever played with a chain or used a bicycle chain? I'm sure you've used a chain.
I know what they are, yeah.
Or do you have a chain like this? It can be straight across. It can be all different ways you can align it, but they're still all linked together. And the way to help you with that one is look at the bond lines. Is this carbon, where's it bonded to, linked to? This carbon. Then it's linked to this carbon. And this carbon is linked to that, and that's to that one. That's why it's 5 carbons. Does that help?
No, I get it once I look at it, but you know, if it was on a test,
well, that's for practice.
It might take me a while.
Well, you got time.
Yeah.
My tests are written, so you have plenty of time. Now, if you still need help and we want to practice it more, can you make it to my office hour tonight? If so, we'll work out something.
Yeah, maybe. Okay.
Right. I'll talk to you after class. But what I'm trying to say is we'll work out a place where we can practice a little with me. Okay?
Okay.
All right. And if we look at B, a ring, we have a double bond. Now in a ring, one of the carbons always has to be 1, the other has to be 2, and you number it in such a way that the alkyl groups also have the lowest numbers. So this is a 6-membered ring, cyclohexane. Don't forget the cyclo for rings. Cyclohexane becomes cyclohexene because everybody knows one of the carbons of a double bond is 1, the other 2 in a ring when there's only a double bond. Therefore, with no number here, and it's always going to be cis in this class and most everything I've ever seen. People know in smaller rings, you don't have to put cis or trans. And then we have a methyl and ethyl. If I call this 1, the ethyl has to be 3. And I have 3 ethyl, 1 methyl. If you put 1 methyl, 3 ethyl, I'm not holding you to the alphabetical rule. That's how you do it. Now, second type of nomenclature question is draw the condensed structure, which means you don't have to show carbon hydrogen single bonds. Like I have here, CH3 is not showing the single bonds between carbon and hydrogen, just condensed. But anyways, cyclohexene, and you could have put the double bond between any 2 carbons. How do you do this? Cis-2-butene, start from the right, move this way to the left. ENEND, double bond. That were ANE, 4 carbons, 4 carbons. Double bond is on carbon 2. It's cis, the hydrogens are on the same side on the bottom, or you could have had on the same side on the top. And if we look at C, which is a little more complex, you start from the right, move left. ENE ending, octane, double bond. That were ANE octane, 8 carbons. Where's the double bond? Carbon 3. 1, 2, 3. I have my double bond, carbons up here, first two. I show my bond angle, which you need to show for sister trans. And notice it's trans, so the hydrogens are on opposite side of the double bond. 1, 2, 3, 4. This comes down here, 5, 6, 7, 8. Then I have methyl CH3, di 2, and they're on carbons 5 and 6. And that's how you do it. Let's go on to the reactions. Again, it'll be, what did I say? I think 47 points on test number 1, reactions. Give the organic product or products for the following chemical reaction. If I look at A, what do I have? Oh, a double bond. What I'm reacting with, hydrogen, a catalyst. Here's the general reaction. Let me remind you, on the test, some of my best students wrote every general chemical reaction underneath. On my test, some of my best students never did. That's up to you. You don't have to do this, but you do have to write the answer. I have this here where I showed it fully condensed. You had a hydrogen coming down here, and this is one, this is one. That would be fine too. Here's the same thing. You break the pi bond. Remember, double bond, 1 pi bond, 1 sigma. Ooh, public service announcement, commercial from Dr. White. For test number 1, and also the other test, remember, how many bonds to carbon? 4. Anybody having nightmares seeing me go 4 bonds to carbon? Hopefully not. But anyways, 4 bonds to carbon. That's going to be your friend. When I'm grading tests for the final, I see a carbon with 5 bonds. One time I saw 7. I almost fell off my chair laughing, and then I marked it wrong because it was immediately wrong. So there's only 4 bonds to carbon. So when you're writing down structure, make sure you don't have 5, because that's going to be wrong. The other thing that will help you on every test, test number 1, when you're doing a reaction, other than combustion, do you break carbon-carbon single bonds? No. I'll say that again in slow motion. Other than combustion, when you burn something, do you break carbon-carbon single bonds? No. So don't. When I started brainwashing students, and that's what I've been doing with this, and no, you don't break carbon-carbon single bonds, scores started going up and grades went up real big time, which is a good thing. All right, so we break the pi bond, hydrogenation, break the pi bond, each carbon double bond gets a hydrogen. This is a ring. And I broke the pi bond, and I don't show hydrogens on there, so it's this way. Now, one of the things a couple of years ago, students said, well, can I use the line method and use the fully line method? At the end of the line is a carbon. So this is another way of writing it. You'd probably see this on Wikipedia or on the internet, other places, but this is the way I try and teach you. It's easier. But if you want to use this method, I am fully able to determine is it right or wrong. Let's look at D. Now here, I've done the favorite trick organic chemist instructors like Dr. White do. I put a big scary molecule, lots of carbons, branching. Oh, no, you look for what's different, double bond. Reacting with bromine, that's a halogen. The general reaction, double bond. Break the pi bond, each carbon gets a halogen. This can be chlorine, bromine, iodine, or fluorine. I didn't write it there, I should have. So I have all these carbons across, I have the same number. I have these 2 methyl groups, they're still there. Here are my 2 carbons of double bond, which is this 2 carbons. I now only have a single bond because I broke the pi bond, and each one gets a halogen. And now, if we look at Next one, like E, double bond. Again, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention because that's where the action is. And I'm reacting with HBr. You should know your halogens, fluorine. Well, this one, bromine, chlorine, and iodine, is abbreviated by an X. And break the pi bond. One carbon gets, where am I? One carbon gets H, the other gets X. It follows Markov-Nikols's rule. The carbon with the most hydrogen gets the H, the other gets the halogen. The rich get richer, poor get poorer. Hydrogens, that is. This has two, this has one. Do you break carbon-carbon single bonds? No. So I have three carbons. This carbon gets the H, this gets the bromine. Now with a ring, Dr. White and Mother Nature love rings. Students don't. Why? Well, look at this problem. Double bond, HX. I break the pi bond. Here are my two carbons. Now, how many hydrogens? Oh, no, it doesn't say. Well, you know, there are four bonds. 3 minus 4 is one hydrogen up here. I should have written it on here. Bad, Dr. White. This has 0. Therefore, the hydrogen will go there. You don't show it. And the halogen goes to this carbon. Put CH2 there and I there. That's okay. This isopropyl group comes along for the ride. And if we look at G, and let's go to I. I put a little more fancy or scary molecule. What's different here? And hopefully that will go away in a second. A double bond. What are we reacting with? H plus, which is acid catalyst and water. And the general reaction is double bond H plus and water. Think of water as HOH. And you break the pi bond. One carbon gets the H, the other gets the OH. And again, it follows Markov-Nikols's rule. The carbon with the most hydrogen gets the hydrogen of the carbon of the double bond with the most hydrogens gets the hydrogen. The other carbon double bond gets the hydroxyl. And if we look at I, the first carbon has 2 hydrogens, second 0. Oh no, don't look. It's a naked carbon. That should be CH3. Oh, I'm so embarrassed. That should be CH3. But anyways, we have 1, 2, 3, 4, 5 across, 5 across. These are my 2 carbons in double bond. This one had 2 hydrogens, so here it gets the hydrogen. This carbon has 0, so it gets the hydroxyl group. Same thing with the ring, 1, 0, hydroxyl group there, hydrogen there. All right, quick question. Any questions about alkenes? Anybody happen to think of a carrot or a tomato and that's double bonds causing the yellow or actually orange or red color? Anybody happen to drive by a gas station or cook with natural gas and think about those are alkanes? Did you light a candle and think about it's got alkane? By the way, this comes from Gouda in the Netherlands. I missed that candle shop. It was so beautiful. It was so small, tiny. My office here was almost as big as that shop, but oh, they had good stuff there. I spent money. Oh, did I spend money there? Yes, I do have a nice candle collection from there. All right, let's go back. Let's look at next set of problems. And here we're talking about alkynes, triple bond. Give the IUPAC name. That means give the official name. I'll never ask you what IUPAC stands for, even though I think it's still cool to say International Union of Pure Applied Chemistry, but I'll never ask that. And how do you do that? You look for what's different. Count how many carbons are in the longest chain that contain both carbons of the triple bond. Remember, triple bond, 2 pi bonds, 1 sigma bond. And this 2, simplest one, ethine. Drop the A-N-E ending, ane, 2 carbons, put in YNE. Now, there's no number here because it's impossible to have 2 or 3 ethine. That's why. Now here, 5 carbons, pentane, triple bond, drop the A in the ending, put YNE, pentine, and it's on carbon number 1, the closest carbon to the end, 1 pentine. For a triple bond, you can't have sister trans. The bond angle is 180 degrees straight across. And the alkyl groups are covered like alkyl groups always are. And let me do D. How many of you put down T-butyl? That was a trick. It's not a T-butyl, it's part of the chain. And here, what's the longest chain? 1, 2, 3, 4, 5, 6. Hexane, it's a triple bond, hexine. From this side, 1, 2, 3. Now this side's 1, 2, 3, but you count from the side that also gives the alkyl groups the lower number. So it's still either way, in this case, 3 hexine. And then I have 2 methyl groups, dimethyl. Remember, whenever you see di, you need 2 numbers, even when they're on the same carbon. So that's 2, 2 dimethyl, 3 hexine. Now, there's only one common name I asked you to learn, and that's this, acetylene. That's the simplest. In IUPAC, it's ethine, but nobody calls it that. Everybody calls it acetylene. Now, let's look at C. If I'm not doing one you'd like me to do, let me know. How do you decode this? You start from the end, move from right to left. YNEN, ooh, triple bond. If that were ANE, heptane, 7 carbons, 1, 2, 3, 4, 5, 6, 7. Triple bond is carbon 3 and 4. This tells you it's the lead carbon. Then carbons methyl, CH3, di 2. And oh, I forgot a dash right there. Don't look, don't look. 2, 5, 2, 5. And that's how you do it. Let's look at the reactions. Give the organic product or products for the following. What do we have here? Oh, let's look at B. Big scary molecule. No, you look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen? You should get your attention immediately. And that's, oh, a triple bond. Reacting with hydrogen excess, and I forgot to put the catalyst on the actual problem set. If I make a mistake during the test, oh, quick thing. While you're taking your test Wednesday after class or maybe Thursday morning, every couple hours or so, or maybe more frequently, till about 10 o'clock at night, I will check my email. Remember I said there's no such thing as a dumb question? Well, that's true while you're taking a test. If you're not sure about something, email me and I'll get back to you. Will I give you the answer to the problem? No. Will I answer your question, try and help you with the confusion? Yes. And here, triple bond, big molecule, but I just see a triple bond, excess hydrogen. Remember, XS in a bracket means all the hydrogen in the world that can react with anything hydrogen can react with, because organic chemists hate to balance equations. We don't have to. Triple bond, excess hydrogen, and catalyst, nickel, platinum, or palladium. You break the 2 pi bonds. Remember, 2 pi bonds, 1 sigma. Each pi bond is a pair of electrons. Each sigma is a pair of electrons. I break the 2 pi bonds, and each carbon of the triple bond gives, say, 2 hydrogens. And you break carbon-carbon single bonds? No. So you have 1, 2, 3, 4, 5, 6 across. 1, 2, 3, 4, 5, 6 across on this carbon. 2 methyl groups still there. Here are my 2 carbons of the triple bond. I've broken the pi bond, and each one gets, in this case, a hydrogen. And go about a minute over, and we'll still take a 5-minute break. And the last one here is I have a triple bond reacting with halogen. I have excess. triple bond, 2 pi bonds, excess halogen, where this can be chlorine, bromine, fluorine, or iodine. You break the 2 pi bonds, and each carbon of the triple bond gets not one, but 2 halogens. And for 3 carbons, break 2 pi bonds. Each one gets 2 bromines. Here, big scary molecule. No, break the pi bonds. Each of these carbon gets 2 chlorine. The rest are still along for the ride. Wow, we've had a busy last 50 minutes. It's time for a break. Let's take a 5-minute break, come back at 1:56, and I'll see you then. All right, ring, 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 ring. Everybody have their 5 minutes. If we're at COD, I see wrong school, ECC, every 50 minutes, I would take a 10-minute break because I've been on my feet for 50 minutes. I go sit down or get water, fill up my water bottle or whatever. But anyways, let's get back to it. Today, we may go a little later. What I mean by later is because I gave uh, taught you the method and things like that. I'll still get you out of here by 3:15, if not sooner, maybe even sooner. But you're supposed to be here with me until 3:50. So, but when we're in a lab at ECC, you get out early too, sometimes, a lot of the times. All right, let's get back to aromatic uh, compounds. Let me remind you, because the test is next Wednesday, a week from today, I'm going to do on Monday. We'll finish today. I'll go through Monday, the aromatic problem set, and I will also do my world famous review for the next test. Yep, it's world famous, man, maybe, but students say it helps them, so I do that. All right, let me just close something out. All right, everybody should see on your screen nitration. Remember, when we have a benzene ring, the double bonds don't want to be broken because they're holding hands, and that gives them stability. When you have a molecule, rarely in a chemical reaction, almost never, you go from a less stable, stable, uh, a more stable to less stable product. So you're not going to break the double bonds in a aromatic ring, benzene. What you will do is substitute one of the hydrogens here with stuff. And I showed you nitration. When you take nitric acid and sulfuric acid, you put an NO2 group. I also mentioned that I will not teach you directors having something on the ring already. So this is the only reaction I can ask you on test one for nitration. Same thing for sulfonation, which I covered. Remember, don't forget this is SO3H. Students forget to put the H here. Say this think that adds, it doesn't. Now let's talk at the new reaction. And this is called Friedel-Crafts Alkylation. Now, for many generations or decades, last 20 years, I think it's died down more. If you or you and someone else discovered a important discovery how to do a reaction, it was named after you. In this case, we honor Friedels and Crafts who came and discovered this or created it, however you want to, because it wasn't slaying on a beach and they found it under a rock. They created it, invented it, but we still use the term discover. And I will never ask on a test what's the name of a reaction, but I do honor Friedels and Crafts by using their name. What is Friedel-Crafts alkylation? This is a very special reaction because of all the hundreds of general reactions, I'm only teach you a little over 50, but I know hundreds of them. There's only a handful, only about 20 or so, where you make something very special, very rare, very good, a carbon-carbon single bond. And this is one of them. What is Friedel-Crafts alkylation? Take a benzene ring, react it with an alkyl halide. Remember, R means anything with carbons or hydrogens. I can have a methyl, ethyl, T-butyl, 100 carbons, whatever. And you use a catalyst, aluminum it should be a small L, which it is, aluminum trihalide, and you put an R group. You make a bond between the benzene ring and the carbon in the R group. Which carbon? The carbon that has the halogen. You also make HX, which is an organic. I had a couple of years ago twins in my class. These two girls were very nice, except they just got bent out of shape if I didn't show the inorganic stuff. I mean, really, they got upset. It was not fun. They learned you don't get too upset around Dr. White, but I figured to keep them happy, I put down the inorganic, but you never have to do this. So let's look at Friedel-Crafts alkylation. By the way, in real life, I've only seen this done with chlorine or bromine, iodine, alkyl halide. I think cost-wise is why you don't see that in real life. So I'm just going to do it in real life because Dr. White lives in real life. All right, let's take a look at a reaction. And instead of writing A plus B plus C, a lot of times organic chemists will do this. What this means is I'm reacting benzene with this compound, an alkyl chloride. Alkyl means an R group carbons and a halogen, and this catalyst. Now, once again, look at what's different. Ooh, a benzene ring. Let me see if I can do, that's a better looking one. What am I reacting with? Well, these are all R. What's different? Ooh, a halogen. And I can abbreviate it like this, where this is my R group. And I have aluminum trihalide. Halogens are that. Remember, X here can be chlorine or bromine. And what happens? I replace one of the hydrogens with my R group. The bond from the benzene ring to the R group will be to the carbon in R that has the halogen. In this case, the end carbon right here. Do you break carbon-carbon single bonds? No. So immediately my general reaction tells me I'll have my benzene ring. Don't forget to put the double bonds in there or a circle. Then I'll have 3 carbons. Now notice the chlorine is to the end carbon. Therefore, the bond to my ring will be to my end carbon. And look what I've done. I've made a carbon-carbon single bond that's very special, very rare, and very good, very useful. And that's Friedel-Crafts alkylation. I see people writing this down, so I'll take a drink of water while you're writing it down. Tonight at midnight, I'll be giving speed structure drawing lessons. No, I won't. All right, everybody got this down? If not, go back and look at the video. By the way, thank you all, those of you who are looking at the videos for Chem 170. That's on my YouTube channel. And today's sometime tomorrow, by the end of the day, I'll have today's lecture posted. All right, let's move on. Let's try another one. Notice I didn't put on the one above HCl because I'm only asking for the organic products. Why don't you try this one? Let's see if you can do it. Just so you, in case you didn't write it down, I'll help you out. Here's the general reaction. And have fun. And if anybody has their dog, cat, or child around, hi from Dr. White. Last semester. Oh, what's the name of your cat? If you don't mind sharing.
His
What?
name's Loki.
What?
Loki.
Floki or Pokey? With an F?
Loki.
Loki. Oh, like the Nordic gods. God of
Exactly.
personal thing. How many people, and Dr. White has a copy of the Prosetta in their home? You know what the Prosetta is? That's the epic saga or tales of all the Norse gods. And it tells the story about Odin, Thor, Loki, Heimdall. Dr. White loves the Norse mythology. So is it he or she?
He's a boy.
Oh, does he cause a lot of problem like Loki? Mischief?
Yep.
Okay. All right, let's get back to our organic chemistry. Thank you for sharing, Justin. All right. My other class, I have a couple of students who have their dogs and also their children who stop by to say hello. All right, what do we have here? What's different? A benzene ring. What's different here? What's not carbon? What's not hydrogen? Ooh, a bromine. And carbon-carbon single bond. It's an alkyl halide, and we have aluminum tribromide. This is my R group. What happens? You replace one of the hydrogens on a benzene with the R group. Carbon with the halogen is bonded to the benzene ring. So I'm going to have my benzene. Make sure you either put a circle or the bonds, otherwise that's cyclohexane, and I mark it wrong. My R group is 2 carbons, and it's to the end carbon. And that's that. Oh, let's do one more. These are fun. Now, sometimes when you don't have enough room above the arrow, you put it first, one of the reagents, like I'm doing now. And why don't you try this one? 3 points each, give the organic product or product for the following. Oh, my heart feels so good. I see everybody working on their problems, doing organic chemistry. With a big smile on your face, please. Got a full house. Everybody's learning organic. Life is good. And when you're done, give me a thumbs up. I see someone's using a different emoji. All right, anybody need more time? I'd say give me a thumbs down, but Zoom didn't put, oh, that's how I'll become a millionaire. Sell Zoom apps with different emojis, like you go like that and all sorts of things. All right, let's get to work. If I look at this reaction, what's different? Ooh, a benzene ring. Ooh, what's this? Look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen? Oh, look, a halogen. This is an alkyl halide. And I have an aluminum trichloride, which is this. Remember, for this reaction, X can be chlorine or bromine. And what you get is Friedel-Crafts alkylation, put on an alkyl group, which we call an R group. And remember, the carbon in R, which has the halogen, is the carbon bonded to the ring in this one. So I know I'm going to have my benzene ring. Do you break carbon-carbon single bonds? No. So I'm going to have this T-butyl group. Which carbon has the halogen? This one. And now, I know there are 4 bonds to carbon, so I can put in my hydrogens. And I've made T-butyl benzene, and that's how you do it. Now, in test number 1, I'm going to have only one for any of the general reactions we've done, and that would be the following. Remember, this is cyclohexane. By putting the lines in, it's benzene. And now this would be 2 starting materials. I'm going to let you try this one out yourself, and then I'll do it. What would be the starting materials to react with aluminum chloride to make that product? Have fun. Hint, look at the reaction, general reaction above. And if you finish, give me a thumbs up. Or if you don't want to, just sit there and wait until I'm ready to get everybody together. This is a sophisticated problem. We're doing some high-level organic chemistry now, and hopefully it's not too painful. All right, I think everybody's done. Let's take a look at this. I'm going to look right here and say, oh, well, this is the product I have. What's different? Ooh, benzene ring. That's something that has carbon-carbon double bonds. Got my attention. This is carbons, carbons, carbons right here. Well, we abbreviate by R in organic chemistry. Oh, look, I have a catalyst, aluminum trihalide, where X can be chlorine, which is in this case, or bromine. Well, what do I react? A benzene ring plus an alkyl halide. Now, the halogen is on the carbon in R that was bonded to the carbon that's bonded to the benzene ring. So one of these question marks is this. Notice I have 1, 2, 3 carbons. I'm not adding carbons, so I better start my second thing, 3 carbons. Now, which carbon has the halogen? Well, which carbon is bonded to the ring? The center one. So that's the one that's going to have the halogen. The halogen is chlorine. I know there's 4 bonds to carbon. And if you react this with this catalyst, you will get that product. And that's how you do synthesis. Now, one of the things I talked about Monday, I haven't put any synthesis problem on the problem set. Just take any one you do, right? Look at the product from the answer sheet, the reagents, and you figure out what the starting materials are. Don't peek, and then when you're done, you can go back and look. And that's how you do those. And let's move on. All right. Next couple of slides, click. I'm going to turn the switch. Will this be on a test or in a final in the off position? However, it's something I do want to talk about because something that will affect is affecting our daily life. Now, we can have in aromatic compounds what are called polyaromatic hydrocarbons. Hydrocarbons, molecules that are only carbon and hydrogen, aromatic, 2n plus 2 pi electrons, poly, many cyclic rings. So that's an aromatic hydrocarbon with more than one ring. And here's an example. I haven't showed you, and also in just general alkanes, this is called the fused ring system. And we'll learn later on, these play a role in our daily life, but I stayed away from it. In graduate school, I worked with this ring system. But today, right now, this is polycyclic, 1, 2 rings. Remember, switches off. It's got 2n plus 2 equal number of pi electrons. And this is called naphthalene. Unfortunately, you're not going to be in ECC, but I have a lab where you smell this. And if you're familiar with mothballs, that's really what mothballs are. Naphthalene's a white solid at room temperature. They take naphthalene, put it in presses to make little balls, and that keeps moths away. Now, why that keeps moths away? Don't know. It's not my area of expertise, but it does. And when I was a kid, you go in my parents' house, they had a closet, which was cedar, which also keeps moths away. That's where you put all your wool stuff, otherwise they ate it. And my grandparents didn't have a cedar closet, but in their bedroom, you could say, what's that smell, Grandma? And she opened up a couple of drawers there. You could see the mothballs in the corners and the wool in there to keep it away. Now, it turns out an important polyaromatic compound is called graphite, which is a form of carbon. And graphite exists as long sheets of 6-membered rings packed on top of each other. By the way, it's used for lead and lead pencil. Since the Roman times, many centuries now, we have not had lead and lead pencils. No, if you stab yourself with a lead pencil, you're not going to get lead poisoning. Trust me, you won't. But anyways, think of graphite as sheets of paper. And graphite is a great lubricant. Why? Because the sheets come right off when they rub against each other. That helps lubricate things. Let me show you an example of that. Everybody see these images right here from Wikipedia? I don't know, did I mention that Wikipedia has been so heavily policed by organic or all PhD chemists like myself? When it first came out, I made a lot of changes or requested them because my credentials, they got changed. But since it's been a number of years now, I've rarely seen a major mistake in anything chemistry. Other stuff I don't know about, but chemistry is pretty good. Now, graphite, you see these stacks here? Think of lots of them, like hundreds. And then if we look at each graphite sheet called graphene, you don't see the double bonds in here, but they're 6-membered rings, sort of like chicken wire that goes on hundreds of these. Now, the force holding the sheets together is very minimal. And that's why it comes off when you write with a lead pencil, which is graphite and other material to make the lead you put in your lead pencil. By the way, Dr. White's been using lead pencils. I still have, which I don't ever let. These have actually a retractable point. The whole barrel comes back in. Well, I shouldn't have showed you that. Now you're going to rob my house. No, you don't. But anyways, these are called graphene. And people thought you could never isolate these separate sheets. People had tried until about, I may be off by about 5 years. It was about 2000, 2005. These two actually physicists who use X-ray crystallographer trick were able to take and isolate individual sheets. How did they do that? Well, the trick they used was they had graphite, they put some Scotch tape on it, carefully pulled it off, took the Scotch tape with one layer on there of graphite, graphene, and put it in a solvent, dissolved it. They won the Nobel Prize in chemistry for that and justly deserved it. I wish I had thought of that. But anyways, now, once you have the single sheet of graphene, you can take it and make the sheet Chemistry Origami 101, a tube. And these are called nanotubes because they're so small. And actually, before they isolated and made them from graphene, graphene, or you can just have the individual sheets. Nanotubes and also the individual sheets are exciting new area in materials in our world. The nanotubes have very strong physical properties, but are super light. So think about a car made out of nanotubes. Your gas mileage would be super high. In other words, you'd get a lot of miles per gallon because you cut the weight from metal. But nanotubes have almost the strength of metal. Now, same thing with graphene, the single sheets, they're very strong. For the last, I'd say 15, 20 years, probably longer, various governments in the world, like the United States, Germany, China, and others, have been pumping billions into nanotechnology research because it's that important. I thought I'd tell you about that. And like I said, nanotubes can be used. One of the problems is they're getting better at it, but it's hard to scale this up, and they're working on it. You can't make a couple 100 million pounds yet economically, but they're working on it. And we're done with the aromatic chapter. Remember, Monday, I will go through the problem set for aromatic chapter, and we'll do that on Monday. I've done it where I've covered everything at least a week before test number 1, and I try and do that. Always cover material at least a week before so you have time to practice, which is why my students do good in organic chemistry and other classes I teach. I'm going to move on to a new chapter. We'll just cover a little of it. This will not be on test number 1. This will be on test number 2. And it's new chapter and functional group time. And that new chapter deals with things that I'll talk about, things that are real stinky. I mean, stinky. I'll talk about things that, one thing that's a very sad tragedy that something good came out of it, but still so sad tragedy. And I'll talk to you about something where if you consume too much of a certain functional group, you can get inebriated. Fancy word for being drunk, which you should never do, but that sometimes happens. And what's that new functional group? It's alcohols. We'll also talk about phenols and thiols. And this is a new chapter. What's an alcohol? Well, up to now, all the things we've talked about, the molecules have that we start with have only carbon and hydrogen. Now we're going to use oxygen, and this is an alcohol. By the way, not all alcohols get you inebriated. An alcohol is any molecule that has a carbon with OH, and this is called hydroxide. I'll never ask that on a test, but OH hydroxide group on a carbon is an alcohol. Now, coming chapters, and I'll change the order sometimes. I'll give you the IUPAC, how do you name it? I'll talk about where do you find this in our real world. And now we're coming to functional groups that have been around for eons, and I'll also teach you common names. Then we'll learn how do you make them, and then how do you react them. And now we're getting into the juicy, fun stuff of organic chemistry. So let's look at an alcohol. Alcohol has a hydroxyl group on carbon. How do you name it? Well, the OH group, hydroxyl group in alcohol, is indicated by changing the end of the alkane name, ANE, dropping the E, and adding OL. The longest carbon chain has to contain the carbon with the hydroxyl group. Use a number to denote the carbon the hydroxyl group is on, and the rest of the rules we've learned about alkyl groups are followed, except the hydroxyl group has higher priority than the alkyl groups, meaning you number that carbon lowest. Now, I'll never ask you these rules, but we'll go through them. I see people are copying. I'll give you a second. Everybody give me a thumbs up when you're ready for me to move on. Okay. Let me check the other group. I guess everybody's ready. All right, let's look at how you do this. Let's do a couple of examples. Then we'll start our lab today, and I'll get you out at a decent time. All right, let's have an alcohol. All right, first thing you do is look at a molecule and say, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? And immediately I said, oh, an oxygen with a hydrogen. That's a hydroxyl group. This is an alcohol. This is how we abbreviate it. Remember, R means anything with carbons and hydrogens. So how do you name this? Well, it's an alcohol. And I'll find how many carbons are in the longest chain. They have the carbon with the hydroxyl group on it. 1, 2, 3, 4, 5. I got the hiccups or whatever. Must be drinking dangerous water. Anyways, 5 carbons. We know that's pentane for an alkane. I'm going to drop the E at the end of ANE. And since it's an alcohol, I'll use the OL ending. So I'll name it pentanol. Now, am I done? No. What carbon is the hydroxyl group on? And you number from each side, and you give it always the lowest number. If I started from here, it'd be 1, 2, 3, 4. So which is the lower number, 2 or 4? And hopefully all pick 2. So that's 2-pentanol. And that's how you do it. Let's go through it again. You find the longest chain that has the hydroxyl group, because an alcohol is carbons with a hydroxyl group, and that's 5. You name it as an alkane, pentane, drop the E, use OL ending, pentanol. And then what carbon is that hydroxyl group on? Let's do one more. Hydroxyl group counts as one bond to carbon. And let's take a look at this molecule. I'll do this one, and maybe not today, but on Monday, after I do my review and the problem setup, we'll get back to this. I'll let you try some too. All right, look at the molecule. What's different? Ooh, what's that carbon-carbon single bond or carbon-hydrogen? Oxygen with a hydrogen hydroxyl group. I have an alcohol. Remember, hydroxyl group on a carbon in a molecule is an alcohol. And how many carbons are in the longest chain with the carbon with the hydroxyl group? 1, 2, 3, 4. Or you could have called this one 4. It doesn't matter. You get the same answer. So 4-carbon chain alkane is butane. It's an alcohol. Because of the hydroxyl group. And I drop the E, add OL, butanol. Now, which carbon is the hydroxyl group on that's close to the end of the chain? Well, it's on carbon 1. That's 1-butanol. As soon as I say that, that's all spoken for. Am I done? Oh, no, look, it's your old friend, the methyl group. And it's on carbon 3, so this would be 3-methyl-1-butanol. And that's how you do it. And I've been able, like I said, on my syllabus, to start this chapter, which I did. We're in good shape. So it means it's time to do today's lab. And let me just close some stuff up here. Oh, one of the things, if you look at, you'll see we went from chapter 4 to chapter 7. Chapter 5 deals with stereochemistry. We'll come back and cover that when we do carbohydrates. Chapter 6 deals with alkyl halides, and we'll cover that throughout the other functional groups. It's better to do it the way I'm doing it as opposed to the way the author does it. Give me a second while I find something. All right, lab time. Get your safety goggles. Oh, we're at home. You don't need them. If we were, after I finished introducing you to today's lab, I would go and ask you to get your goggles on and we go into the lab and do this. I wish we could do this, but there's no way to really easily do virtual organic chemistry labs at home or deal with chemicals because it's dangerous. Anyways, today's lab deals with alkanes and alkenes. There's not much I could find doing triple bonds, but single and double bonds. Now, the way I've written the labs, if we were at ECC or you'll be doing it, I try and give you everyday experience. Sometimes you can pull it off online. Sometimes I got to help you out and give you some of the data. But before I do that, don't forget, hand in by uploading it to the assignment areas, a PDF file, the melting point lab that's due today. If you get it in by tomorrow morning, it's okay. But get it in or you'll lose 10 points. And you don't want to lose 10 points. There's 11, one of those two. And so please do that. All right, let's talk about today's lab. Today's lab will look at alkanes and alkenes. Alkanes, carbon-carbon molecules with only carbon, hydrogen, carbon-carbon single bonds, and alkenes, double bonds. Now, in the assignment area, I have this lab posted both as a PDF file and as a Word document. And what the first thing I did, if we had done this in the lab, you'd go into the lab and you'd smell things. And odor is an important part of organic chemistry. And what I did is, here would be the things you would test. You put some, if it's on a liquid, on a small piece of paper, step away from the fume hood, and then put the paper towel under your nose, or you could have also done it like this, but since you're not doing it right over the bottle, by putting on a paper towel, you can do this, or you can still do this way, and you smell it. Now, one of the things I've done is, I remember what students normally say it smells like, and here I have the chemicals you would test, and here are what they smell like, or what students think they smell like. And that would be part 1. Now, part 2 and 3 deal with tests used to identify functional groups. Now, not until the late 1950s or 60s, and even not until the 70s, when I was in grad school, we started having what's called electronic instrumentation that allows us to identify things, and it's amazing. Unfortunately, I can't teach that. I don't have the time to teach like infrared spectroscopy, Fourier transfer, near infrared, FTNIR, or proton nuclear magnetic resonance, or carbon-13 nuclear magnetic resonance. Dr. White knows those, but and I've used them, but for this class, I'm staying away from it because I only have 16 weeks to teach and not 2 semesters. 2 semesters, we'd be learning it. However, back before we had that electronic equipment to help us, we had visual tests. You mix things together, see a color change. When a really good physical test is, does that molecule have a double bond or not? And that's used the following physical test. And here I'm showing you the general reaction. You take a double bond, any double bond, that's why I have R and R prime, and react with a halogen, it reacts immediately. Now, for this lab, what you'll be doing is, if you have a double bond and react it with a bromine solution, this is a red color, red or reddish brown. And if it reacts with a double bond, you break the pi bond, and from this reaction, you know, each carbon, in this case, will get a bromine. Now, these compounds are either colorless or slight yellow color. So if I have a test tube, Dr. White will never be an artist. You can laugh your head off now. And I put in some of my BR2 solution. This is abbreviation, which is reddish brown. If there's double bonds in here, it will react and the color of the solution will stay either clear or slightly yellow. If there are no double bonds, it will turn a reddish brown. And right here, I have a YouTube video that you can watch that shows this. And what you'll be doing is working with this. Actually, because of the problems I had at the other school doing this reaction, somehow, and it happened twice, and I know why, by accident, one student got the bromine solution, which will burn your skin pretty bad, on the back of a neck of another student. And after that, I said, no, I'm not going to have students messing with bromine. I know how to handle it, but they have trouble with it. So I'd actually do a demonstration. And you'd watch me do this. That way you're safe, I'm safe, and Dr. Whitehart feels not too bad because everybody's safe. Now, if we were to do this in the lab, cyclohexane, no double bond, and you would see when I put the bromine solution in there, it turns red-brown or reddish-brown. 1-hexene, ooh, it's got a double bond. And when I put it in there, it reacts and stays clear. Octene, and depending on what we have in the classroom, in the storeroom, sometimes this is 1 or 2 octane, and it stays clear. Now, I talked to you about limonene, and that has a double bond in it, and that stays clear. Now, to make this interesting, when we're in the lab, or now, we have 2 unknowns, cleverly labeled unknown A or B. And later on, you've got to determine what functional group is in here. Don't give it away, please. Don't say it in the chat. And A would be, if we put the bromine solution, stays clear. B goes reddish brown. And then I teach you how to clean this up and show you where the proper waste bottles are, but we're not going to do that now because we're not in lab. And you'll need this data later on to answer some questions. All right, that's that part. Remember, the bromine solution is a reddish brown. When you react it with anything with a double bond, it forms this compound, a dibromide, and or dibromo, and it becomes colorless or very slightly yellow. If there's no double bond, its solution turns red-brown or reddish-brown. And like I said, you can see this at your leisure. I'll let you watch this on your own. Now, let's go on to part 3. And this is also another way of determining, does a molecule have a double bond in it? Now, it turns out there's a series of reagents which we call oxidizers or oxidizing reagents or oxidants. And potassium permanganate, KMnO4, in solution does that. Now, a double bond, most organic compounds, most of them, and the ones we do, are clear or slight yellow. Potassium permanganate solution is purple. I mean, a really beautiful purple. Now, this reaction I didn't teach you in the classroom, so I'm trying to keep down to things that are important. But if you have a double bond and react it with potassium permanganate solution, it oxidizes it, and you break the pi bond, and each carbon gets a hydroxyl group. Now, this is colorless. Otherwise known as clear solution. But you get something else. When this is oxidized, this is reduced. And what you get is manganese dioxide, MnO2. And if you see this, it has what I call a muddy brown color. And if you go to parts of the United States where they have a sort of brownish dirt and you put a little water in there, that's what manganese dioxide looks like. So if you take a molecule and it has a double bond, this solution is purple. If there's no double bond, the solution stays purple. if there's a double bond, you'll see a muddy brown color because of magnesium dioxide, MnO2. And here's a YouTube you can watch to see that. It's a lot of fun to do this. I wish we could be in the lab, but I decided to make this class all online, which I think is better for Dr. White and maybe you too. So here, you would do this yourself in a test tube. You put about 10 drops of the dilute potassium permanganate solution. That should be a subscript 4. Add about 5 or so drops of whatever liquid you're testing. Shake it. Wait up. You don't even have to wait 3 minutes, but wait 3 minutes and mix it. And then wait 10 minutes. Now wait about 2 minutes after you mix it and observe it. And then I show you where to put the organic waste from the empty the test tubes. And if you were in the lab, you'd be testing cyclohexane, no double bond. Oh, look, it stayed purple. 1-hexene. Ooh, double bond, it went muddy brown. Either 1 or 2-octane, double bond. Limonene, double bond, went muddy brown. I'm not going to tell you and don't say it. You have to determine when you did a unknown A and B, does it have a double bond or not? And hopefully I've taught you now. And here I asked you to draw the structures of cyclohexane, 1-hexane, octane, 1-octane, limonene, and naphthalene, because you need those to help answer questions. Then here are the questions there. Remember, this is due. Now look at question 4. Please identify unknown A and B as either an alkane, not the stuff above, but is it either an alkane, no double bond, or alkene, double bond? And you describe what data and the results from tables 2 and 3 allow you to make that. So there's 2 things you have to do. Is the A have an alkane, is an alkane or alkene? Is B an alkane or alkene? Identify these, then explain why you did that. All right, that's today's lab. No, I'm not done yet. Right now, I'd like to do an experiment with all of you. One of the problems with being online is if I were in the lab, I'd be walking around talking to you and get to know you. I can't do that. And you'd get to talk to me and get to know me. Well, you've gotten to know me a little, and you really can't do that. So how are we going to get over that? Well, let's try breakout rooms. Since we got a small class, I'm going to put 4 in one breakout, 5 in the other, and we'll switch in the future. Let's see how it works. When I put you in a breakout room, this will only be about 5 or 7 minutes. Say hello to the other people.